agenda. You don't have any homework due tonight. Your homework's due Wednesday night. Not that anyone's excited about that. Just saying. And in case you've forgotten, there's no class Friday. I had it canceled for the entire college. I went on my way to make sure that happened. So, because there's no class Friday, it means no quiz on Friday. And it means there's no quiz next Monday, because I try not to have a quiz after a little break because you guys always do terrible. So it seems like no point in having that. So, alright. So, last time we left off, we were looking at dispersal of matter, right? We had those energy level diagrams. We were talking about energy at the bottom versus at the top, and you can spread it out a bunch of different ways. And the more pieces of matter you have, the more ways you can spread it out, and some become statistically more probable than others. What we're going to do today, for starters, is do some graphical practice at this. So, one, if you have more than one color in your backpack, pencil, pen, something, you'll need at least 2, maybe 3 different colors. Or you can do different shapes, whatever you want. And you'll need your calculator. So this will make more sense when we start doing it. But if you have more than one color, it's easier. Alright, so for matter, right, it's really hard to think about energy level diagrams and how easy it is to move from one energy level to a tricky. It's tricky to do that. So we're going to just look at dispersal of matter in a given set system. So we had on Friday, right, that little flask that had the little stopper on it. Right, I had a little stop, and I had gas just on one side, and I could open up the stopper and you can move to both sides. So let's draw. I'm going to have just 2 molecules for starters, right? I'm going to have a green molecule and a red molecule. If you don't have different colors, you can do different shapes. That's fine too. Alright, so this is initial. Alright, so let's say I open up the stopper. Or I take out the stopper, however you want to think about it. Stopper's gone. What is one possible thing that could happen to those 2 molecules? They could both go to the other side. That's fine. They both move. Okay, what's another option of things those molecules could do? So do you care which side is which? Okay, we could do, my dumbbell starts to look crazy after a while. Right, and then the fourth option is that they don't go anywhere, right? Okay. Oh, excellent question. Let's think about that. Alright, so I have 2 different molecules and I have 4 different ways I could get them to move around, right? They all go, they all stay, one goes, or the other one goes. Okay. So if I have 4 different options, what is the probability that this one is the one that happens? 1 out of 4, right? 1 out of 4 chance. What about this one? What about that one? 1 out of 4, right? 1/4 chance of any of these. Okay. Okay, so I have a 1 out of 4 chance of any of them. Which 2 are practically identical if I number them? Right? Number 1 and number 3 are practically identical, right? Because the 2 molecules are the same. It could be nitrogen or oxygen, right? The molecules don't It's the same one on either side. So what's the probability that number 1 and number 3 happen? Right, 1/2 or 50%. Oh, there's a D in probability. All right, 50% chance that 1 or 3 happens, and 3. So out of our 4 options, what is the most likely scenario? They all stay, they all go, or one goes? One goes, right? Based on your probability statistics, right? The most likely is that one of the molecules moves to the other side. Doesn't matter which one. That's a 50% chance. Somebody's going to move and somebody's going to stay. All right, well, let's think about this in terms of mass. All right, how many molecules are in my flask? 2. All right, 2 molecules. How do I get to 4? Like, if I have the number 2, how is 2 related to 4? 2 ways, right? It could either be 2 times 2, or more likely, it's 2 squared. So this 2, this bottom 2, right, that's the number of sides of the flask, right? It can either be on one side or the other, right? There's two lobes. And then this number 2 is the number of molecules possible, right? So that's statistically 4 things that could happen, right? Four things. And it comes from 2 sides squared. That's like baby steps. What if I had 3 molecules? Okay, so let's draw that. I wrote way too big, so I'm gonna draw it over here. All right, so now we're going crazy. I'm gonna put 3 identical molecules. Put my stopper back in. It doesn't, but man, it gets complicated if it's more than 2. So for now, we're just gonna do 3 molecules. All right, so I have 3 molecules stuck on one side of the flask. I open my flask. How many different choices of flasks now do I have to draw? 8, right? Because now I have 2 cubes. That side, that's number of molecules. Cubes. Which means I now have 8 options of things I can draw. Oh, something like that. Okay, they're getting a little crazy looking. Alright, so why don't you take a minute or 2 and see if you can figure out what the 8 different options could possibly be. Any combination of 1 going, 2 going, all staying, all going. See if I can figure out all 8 also. Yep. I realized after looking at my computer screen, the green kind of looks like blue. Alright, so I have 8 different options, right? Alright, so what is the chance that I end up with this configuration? The green's on one side and the blue and red on the other. What's my probability of getting this one configuration? 1 out of 8, right? 1 out of 8 chance. What about this one? What's my chance of getting that one? Also 1 out. Okay, good. What about this one? Also 1 out. As soon as someone answers, I'll stop asking. What about this one? Okay, good. Alright, what is the chance that no molecules move at all? Okay, also 1 out of 8. What are the chances that all the molecules move? So, statistically, what is more likely? That nothing moves, everything moves, or any other combination? They're all the same, but, right, these all have some combination of opposites, right? Like this is nothing moves, this is everything moves. It's more likely that some of them move, right? Looking at the boxes. How much? 1, 2, 3, 4, 5, 6. 6, 8, 4, what is that? So about 2, 3, 4. Right. So it's a 3/4 chance to have some sort of distribution of molecules. Right. This one says they all are in the one side, this all on the other. More likely if they're going to kind of separate themselves out. Some go, some stay. Alright, good. At this point we're going to stop drawing and move over to our calculator. Because I want to know okay, what if I now have 20 molecules? What is the chance or probability that no molecules move? Alright, so how would I figure out how many different flasks I would have to draw? What would I figure that out? How did we figure that up here? Okay, so now I want 2 to the 20th. Which your calculator might fight back a little bit about. Should be 10,000, no, 100, no. Yeah, there we go, 1,487,576 flasks. We would have to draw that many flasks. Yeah, that'll be the rest of today. No, so what is the chance that the molecules do not move from their original flask? 1 over, so the answer to this question is 1 over 1 million. What is the chance that they do move? What are all the chances that they do move? It'd be 1,048,000, yeah, minus 2 over here, so 574. So what's more likely? They all stay or they all move? They all move in some sort of combination, right? They distribute themselves. Okay, how many molecules are in a mole? How many molecules are in a mole? Oh, you guys are you're messing yourselves up. What Avogadro's number? Okay, wow, okay. I was like, okay, let's move back to 108. Okay, so how many molecules are in a mole of molecules? Okay, whew, okay. Like I'm getting all sweaty up here. I'm like, you guys have nothing. Okay, now we're good. Okay, number. You guys are totally reviewed. Okay, molecules in a mole. All right, if you don't know this, star this. You'll need to know this pretty much the rest of your scientific career. Right? Okay. Right, so I had 2 molecules, I had 3 molecules, I had 20 molecules. Okay, now I actually have a mole of molecules. How would I figure out how many flasks I would need to draw to represent a mole of molecules being distributed? You can certainly try putting this in your calculator. It'll just give you an error message. I had to go to Wolfram Alpha to get the actual answer. This happens to be easy enough. Let's see. Oh, there we go. 10 to the 10 to the 23rd. So 10 raised to the power of 10 raised to the power of 23. The computer got kind of angry when I was trying to get. I was like, no, I want it as a decimal. No, not going to happen. So what are the chances that the molecules, a mole of molecules, don't move? A tiny, insignificant likelihood, right? What would we pretty much call that chance? 0. What would be the chance of all the molecules moving from one side to the other side? Also 0. So it feels all moving or not moving at all. It's pretty much 0, right? Imagine it's like your chance of winning the lottery. Certainly a chance you win the lottery. Realistically, 0 chance of winning the lottery, right? So, what was the point of all this? I'm glad you asked. Alright, so it's much more probable Alright, so it's much more probable for the molecules to distribute themselves between two flasks, rather they're not going to stay all together, they're not going to move as a group. They're going to choose to distribute themselves between the two flasks in this case. So how does this relate to everything else in the chemistry world, right? So, if we look at just the basic idea of moving things from one side to the other, it relates because the entropy of a state increases, right? So entropy is the number of ways I can distribute the energy. And the more ways I can distribute the energy, the bigger the entropy. So the more molecules, the more likely they're going to want to distribute. So entropy of a state increases with the number of energetically equivalent ways to arrange the components of the system. So let me translate that into non-fancy lingo. Well, I mean, I don't like to use disorder because it's not disorder. It's like everything's still ordered. It's the number of ways I can best distribute my molecules amongst the greatest amount of energy, or number of places. Like in this one, we're just looking at, they could either be all together on one side or all together on the other side. The entropy is better if they're some in both. Yeah. All right, so if you have a state in which a given amount of energy is more dispersed, then this state has greater entropy than a state where the energy is concentrated. So it sounds like disorder, right? I want to have a state where things are less organized. They're not less organized, which is how they're often described. Like entropy is not organization. I just want, if I have 10 kilojoules of energy, I don't want to keep all 10. It's like, if anyone's taking personal finance in here, right? You want to disperse your retirement funds amongst a variety of different stocks and bonds. You don't want to keep all of your retirement funds in one group. You do better if you disperse it amongst a bunch of different things. That's entropy of money. This is entropy of molecules. I want to spread my energy amongst a bunch of different states rather than concentrating it all in one spot. Yes. Yes. Alright, so the second law specifically states that for any spontaneous process, the entropy must increase. Right, because it's spontaneous, it's going forwards, which means that it's more likely to disperse its energy amongst a bunch of different things. So, we write that mathematically by saying delta. What does delta mean? Big delta. Change, right? Big delta. S is entropy in UNIV, universe. So the change in entropy of universe is always going to be greater than 0 if the reaction is spontaneous. Right. So it comes from the fact that, right, delta S is a state function, so it's just final minus initial. So if delta S is positive, which of these two values must be bigger? Final, right? That's the only way it works out. Right, so you want delta S positive for spontaneous, which means your final entropy must be bigger than your initial entropy. So you ended up with more dispersed matter or energy. I wrote more thoughts. I got more thoughts about this. Hold on. Alright, so the second law explains that the first law alone cannot. What is the first law of thermodynamics? Right, okay, so this one is total energy of the universe is constant. Right, there's neither a loss or gain, it's all, the universe has a set amount of energy. So if you gain it someplace, you lose, all evens out. So, how can we think about this in terms of a practical application and figure out how this works? So, over here. Because they seem to not tell you anything about similar things. That would be incorrect. They totally do. Alright, so let's think about my ice cube and water again. Which direction does heat typically travel? High heat to low heat or low heat to high heat? High to low. Okay, good. So if that was the only fact that was true, okay, what happens to my ice cube? Does it become liquid or become more solid? becomes a liquid. So which direction does it have to give off energy? Okay, so if that's true only, then right, the ice cube would lose heat, right, and then the water would gain that heat. Which we know is totally not true. That's totally incorrect. We only had the first law of thermodynamics. Because what would this tell you at the water's temperature? If it gained heat, would it get hotter or colder? It was getting hotter, and what's happened to my ice cube? It's getting colder. That would be amazing if that was actually the case, right? You could put an ice cube in the water, and the water would get hotter. We know for sure that's not true, but that's what, if we only had the first law about energy being constant, that's what we'd end up with. So we need the second law to tell me about which direction is that energy traveling to make things spontaneous. Now, let's talk about that. Changes in state and energy changes. Alright, so the biggest thing that happens when you change states of matter is the entropy of the sample will also change. So let's think about, we'll do this one. Let's say I'm going from a solid to a liquid. What is happening to the movement of a single molecule? If it's in a solid, how much can it move? A lot or a little? If your molecule's stuck in the middle of an ice cube, how much can it move? Not at all. What if now I have a piece of molecule stuck in water? Can it move more or less? More, right? Okay. So how much energy would it have? More or less than the ice cube? If you have more energy, I have more places to put that energy, right? More ways to distribute, either in motion or ways I can interact with other things. So if I go from a solid to a liquid, my entropy has increased. Right, because I have more energy, so I have more places to put that energy, I have more moving around, enjoying floating around. Alright, so then what should happen to the entropy of my molecule if I now move from a liquid to a gas? Has my entropy increased or decreased? Increased again. This chapter is miles different than anything we've done so far, right? Because it's all thought. Very little math in this chapter, so it's all about thinking about which direction things are going. So it's going to take a little more reading and practice on your part just to be thinking about these questions. You can't mathematically prove really much of anything. So, depending on what kind of studier you are, just keep that in mind. Alright, so, do I want to do this thing? Yeah, okay, we'll do that. Okay. Alright, let's say I have iodine gas becoming iodine solid. Has my entropy increased or decreased as I go from a gas to a solid? It has decreased, so should that be positive or negative? Okay, good. Right, that's a negative change in entropy because you are forcing the molecules to stay in one place. So you are concentrating their energy into one location. So that is negative entropy. What if I have now I have liquid water becoming vapor. What should my sign of delta S be? Positive. Right, because now I have the molecules farther apart in space, more space to put the energy, lots more options. Alright, this is going to be my tricky one. Alright, have I changed states of matter? No. What has happened? Right, I've broken into how many molecules I had to begin with? Well, 2. Right, I have 2 molecules. How many molecules do I end up with? 3. Do I have more or less places to put energy? I have more, right? I only had 2, but now I have 3 molecules. So if this had 10 joules of energy amongst 2 options, now I have 10 joules of energy amongst 3 options. So I can distribute the energy in more different ways. So what should the sign of delta S be? Positive. Okay. Good. Good, good. Alright, so those are all either changes of state or, you know, same state but looking at more places to put it. Let's combine it with some things we know about heat. Alright, so what letter of the alphabet do we usually associate with heat? H, right? This is talking about what word goes with this. Starts with an E also. Enthalpy. Alright, so, just as a reminder, H. The way I keep in mind, right, enthalpy has an H in the word. That's the one that is an H. They both start with E's, and after a while you get confused. So enthalpy has an H, and that is H, that is heat. Entropy is S. Alright, so we can have spontaneous processes that occur even when I have a entropy decrease. So, like the X cube, that's exactly my example. Alright, so I have water freezing to 0 degrees Celsius. Is that an increase or a decrease of entropy? Freezing. Right, so my entropy of water is definitely negative because I'm forcing the molecules to become a solid. Is this a spontaneous process though? If I'm at 0 degrees Celsius, does ice form? Yes. So if I know that this process is spontaneous, what is that S equal to? Greater than 0, less than 0? Okay. If I was going to use the same words I talked about enthalpy, you're either the systems or the surroundings. We do the same thing in entropy. In this case, what is my system? Water, right? So if I have an S, I must have a surrounding, systems and surroundings. What must these add up to then? The universe. Alright, so how we define the universe is just, it's either the thing you're looking at or it's everything else. So it's one option or the other. Alright, so we just said that this one is negative, but we know that this is positive. So what must be the delta S of the surroundings for water freezing? for this final answer to be positive, what must delta S surroundings be? Big positive. And so the reason why is because freezing is an exothermic process, and exothermic, right, means giving heat to the surroundings. Now the surroundings have a lot more energy, and it's going to distribute it everywhere. So it's going to be a large positive. So what is the key factor in figuring out what the delta of the universe is? What if I was talking about water freezing at 70 degrees Fahrenheit? Is that spontaneous? Can I spontaneously get water to freeze at room temperature? Can I spontaneously get water to freeze at minus 273 Kelvin? Doesn't exist. The answer is yes. Right, so the key factor must be temperature. Thanks for playing along. I'm asking a lot of rhetorical questions today. They must be so obvious that you're like, oh, it's the temperature. Alright, so if freezing increases the entropy of the surroundings, why would water not freeze at all temperatures all the time? Spoiler, right? Temperature dependent. So it depends on the temperature. Alright, so let's look at that is my equation to determine the overall spontaneity of water freezing. Water turning to a solid, well, what sign do we give that before? Positive, negative. This delta S system, what was that 2 minutes ago? Right, that's negative. Will that ever be positive? Will water turning to a solid ever be a positive? No, that's negative all the time. So let's look at this delta S of surroundings. It is going to be positive all the time, but what did it have to be for the overall, right? We said it had to be a large positive for this to be positive to overcome the fact that it's a negative value. Right, it has to be bigger than the delta S of system. If you were at low temperatures, let's say 0 degrees Celsius or maybe minus 20 degrees Celsius, it is a large value. Right, because it's putting heat into the air, and so the heat feels much bigger when it's cold outside. But now let's say we're at room temperature. It's going to be a much smaller value. To the point where it's going to be less than the delta S of system. We're going to come over the tipping point, at which point that's no longer less than 0. Yeah, you can. Yeah. We're going to get to that. The will it want to or not. Because entropy is just part of it. Like, if air is already warm, like it is in here, then it's not going to gain anything from getting warmer. Like, right, the molecules aren't going to get much faster. Yeah. Alright, so that's all great. So let's do some quantification. Let's put some numbers to it. Depends on what you're looking at. Yeah. Alright, so let's say you have a system exchanging heat with its surroundings, right? It has to change the entropy of the surroundings, which we just talked a lot about. At constant pressure, we can use little q subsystems. What does little q a measure of? Thinking all the way back to last time you took 108. What's q? Heat. Q is heat. So Q is a direct measure of heat of the system. So let's think through how this will help us calculate things, and then we'll get to the point where we actually calculate. Maybe, when we only get to the point. Okay. Alright, so how is Q of the system and entropy of the surroundings related? Alright. Alright, so if I have a reaction that emits heat to the surroundings, is that exothermic or endothermic? If the surroundings get hotter. Exothermic, okay. If it's exothermic, is that a positive or a negative heat? Negative. This is where it gets tricky, they're opposites. Like, exothermic gives off heat, that's negative, the delta S, the spontaneous, anyway. The system is the thing that's giving off heat. So I always think about it as a beaker. Like, imagine I have a beaker, and that's where my reaction is, that's the system. Everything else in the room is the surroundings. So it's the air, the water, or whatever else. In my head, that's the easiest way to think about it. Alright, so if I have an exothermic reaction with a Q less than 0, what has happened to the air surrounding my really hot beaker? It's heated up, which means it increases the entropy of surroundings. Which means my change in entropy of the surroundings must be positive. So it's gotten more entropy. Any guesses on what the opposite should be? If I have an endothermic reaction, what happens to my delta S of surroundings? Right. So just rewrite all this, but with the opposite words. So reaction that absorbs heat from surroundings. That would be endothermic. Has a Q system greater than 0. Decreases entropy surroundings. So they must be related in some way, right? Because they seem to have, how would you relate these two? They are directly proportional or inversely proportional? They are fairly inversely proportional. Right, because if that one changes, they have opposite signs. Because we didn't have anything about temperature dependence. If I know about their temperature, now I can say things about them. So, I'll leave you on a cliffhanger there. Come back on Wednesday and we'll talk about mathematically what's the equation that relates them. And then how can you use that in everyday calculations if you're just sitting around being like, hey, I wonder what the entropy of the system is. given them at room temperature and stuff.